Moving on to the other transformations, we have scaling and translation. I don't call translation position like we usually see, just because to me, position is the property of occupying a location in the coordinate system. And translation and scaling are geometric transformations that are going to change that property. So scaling changes position through multiplication, and translation changes position through addition. If I open up here the compound, we can see that the scale input goes into a multiply node and the translate input goes on to an add port, an add node. So whatever I plug here into the scale port, I know it will be multiplied onto my input value. So in this case, I have 2, and I can multiply it by 1, or by 2, or by -1, or I can say that I'm scaling it by something, like in this case 0.5. On the other hand, I know whatever I plug here on the translate port, it's going to be added onto my value. So I'm adding 1, adding 2, adding -1, etc. Or I can say I'm translating the value, or I'm moving the value, something like that. Of course, the position is correct. It's just the way that I decided to phrase it. But the same way that we know is we understand in this case, because I can open the compound with what type of operation the values will be used on. There's a lot of parameters and data that we know. We grasp in which operations they will be used. So for example, I know that my reflection buffer, sorry, let me write this again. My reflection buffer will be added onto my image composition, while my diffuse buffer will be multiplied onto my image composition. So we can sort of grasp the operations in which data must be applied onto. So I'm going to do a side-by-side comparison between additive and multiplicative operations, because there's some analogies that can be done. So they both have an identity. In this case, we have that anything plus 0 is equal to itself. So the identity of additive operations will be 0. On this side, on the multiplicative side, we have that anything times 1 is equal to itself. So the identity of multiplicative operations will be 1. And we can look at these as sort of the reference values by which we judge other values, or the starting position. So here we have 0, and to the right of 0 we'll have the positive values, and to the left of 0 we have the negative values. And I know if I want to do through translation to go to +5, I just translate 0 by 5. Or if I want to go to -5, I just translate 0 by -5. So it's, you know, whatever the value that I put on these transformations, it's going to give me the value itself. And on the other hand, here I have my starting position, or my reference value, is going to be this unit vector that goes from 0 to 1. And so I still have this notion of negative and positive values, but what matters here, what's being compared, is the length or the scale of the value. So I have these areas here that from 0 to 1, the length will be less than my unit vector, and from 1 to infinity, the length will be greater than my unit vector. And the same thing will reflect on the other side, but into respect of -1, in the case I have a negative value, for example. So they share a property in which they are commutative. I'm going to write it here, commutative. And what this means is that the order of their operands doesn't matter. So this is a bit relaxing. Say that I have A equals to 2 and B equals to 5. And so I can say that A plus B is equal to B plus A, which is equal to, using these values, it's equal to 7. And on this side, I can say that A times B is equal to B times A, and using these values, this is equal to 10. So this is relaxing because, for example, I have these nodes by Akira Azagi, add 4 and multiply 4, and I can, for example, plug these values here onto these ports, and I get 2, and regardless of the order by which I organize the inputs, I'm always going to get 2. So it's very relaxing, no concerns about order, and no errors. I'm not doing any mistake here by changing the order. So there's another note about the multiplicative side, is that anything times 0, it's going to be 0. So here I have some concerns. And the concern is sometimes I can have a ninja 0 showing up in one of the evaluations of my node tree. And that will mean that regardless of whatever I throw in there, I'm always going to get 0. And sometimes this is not something that I want, right? Because this basically means that 0 is not scalable. So if I'm talking here of geometric transformations, and I'm talking of multiplication as scaling, this means that 0 is not scalable, regardless of of what I throw in here, it's always going to be 0. And we can look at this problem if we looked at the position vector. So I said that it had 2 points, the tail in the head, and the tail was bound to the origin. So it's always 0. So if I make the head also 0, this means that the vector goes from 0 to 0. So it has no length. And it also has no direction because 0 is neither negative or positive. So for something that I said it has some length or magnitude and a direction, this has none. And it can be problematic because, it's not scalable, but also for, say, calculations that need direction. Let's say when we get into 3D vectors, we have, trying to calculate the angle between two vectors. And if one of them has no direction, then this operation is invalidated and, it's not useful. So it's good at times to check for this case, for 0 when we have a data stream. Of course, if I'm using a constant node, I just have to change, but sometimes you have a data stream that we have no control over. So it's good to use a logic node and check if there's a 0 that's going to show up. And if there's a 0, then we want to output a value that is friendly for our operation. So in this case, maybe the operations we are going to do next are multiplicative. And so it's nice to have the identity output. So in this case, yeah, if this is equal to 0, I want to output 1. If not, I just want to output whatever value that I had because it's okay, it's not equal to 0. So this is something that we've done previously, but it's always good to remember. Okay, so now I'm going to look into the inverse operations. And so in this side, we have the subtract node, and this side I have the divide node. And so they perform the inverse operation. So let's see, if I have here 0 and I came to 2 by adding 2, I'm going to go to -2 by subtracting 2. So they perform the inverse action in a way. In this case, here we have the unit space. And so we have 1, 0, and 1. And so if I multiply this vector by 2, I'm going to go to, let's see, 2. But if I divide it by 2 instead, it will perform the inverse action. It will go to 0.5, so divided by 2. So inverse actions with the inverse nodes. So another thing we can see is that they are not commutative. These operations are not commutative, even though they share the same identity. So if I do anything -0, it's going to be equal to itself. Or this side we have that anything divided by 1, it's going to be equal to itself. When I change the order, this is not going to have the same output. So the identity minus anything, it's going to give me the opposite of my input. And the identity divided by anything is going to give me the multiplicative inverse of whatever was my input. So with the inversion, the value inversion here, I get the additive inverse or opposite, and here I get the multiplicative inverse or reciprocal. And we can see this again in terms of order matters by looking at these operations with two values. So let's say I have a equals to 2 and b equals to 5. And so I can say that a minus b is different than b minus a. So this one will be equal to 2 minus 5, which is equal to -3. And this will be equal to 3. And on this side, we have that a divided by b is different than b divided by a. So this is going to be equal. This one is going to be equal to 2 divided by 5. It's going to be 0.4. And this one will be 2.5. Okay. And so what we can also see is that depending on the order of our operands, we get the inverse. They give us inverse of each other. So this value is the additive inverse of this one, and this one is the additive inverse of this one, and this one is the multiplicative inverse of this one, and vice versa. So this means that we have to be really careful about whatever we plug in on subtract and divide nodes or that internally use those operations. So of course, if I plug this in here, I get 1.5, but if I plug this in here, I get minus 1.5. And this sometimes can be really frustrating because imagine that this is something that it's common to me. When I do a wrong assumption of what's the correct order, I start to build an operation and something, everything should be working, but it's not working. And I just, what's going on? And sometimes just doing this, suddenly everything works. And it's like, wow, okay. So that's the good thing about nodes. Sometimes you don't have to be really smart and to know beforehand what's the correct order. You can just, brute force and see if something just works by changing the order. So when let's see two examples of things that these having the inverse value is useful. We can, for example, say that I have a node that has a port that I know it will be, let's say in this case, it's going to use my value in an addition. But I have a data stream of values that actually should be used on a subtraction. So if I plug this in here, this is not going to perform as I expect. So in this case, in between, I'll have to get the opposite of the values. So when this goes out, it can be actually plugged onto an addition, but actually perform subtraction. So by getting the inverse value here, I can sort of like subvert the internal operation of the node. So no longer this data stream will work as an addition, but it will actually work as a subtraction. Same here. Let's say that I have a node and I have a port that I know whatever I plug in here will be used in a division. And I have a data stream that actually should be used in a multiplication. So there's a mismatch, but I can get my multiplicative inverse. And of course, now with this, I can plug this onto a division, and that will actually perform what the values need. So this is a way to, there's a blend here, between value and operation in a way. So sometimes it's like the unitary, it's like the sign or something, and sometimes you look at these as operations. So sometimes the boundaries kind of blend. We can see that in another example. Let's say that I do 2 minus 3 plus 4 minus 5, and on this side I do 2 divided by 3 times 4 divided by 5. Okay, so I cannot swap 2 and 3, and I cannot swap 3 and 4, for example. It will not give me the same output. And I can check that by basically building that in nodes just to grasp it. So I'm going to put these in order here, and I'm going to assign the correct value. So this one will be 2, this one will be 3, this one will be 4, and this one will be 5. And I'm going to need an add node and 2 subtracts. So I'm going to do the additive example. So 2 minus 3 plus 4 minus 5 will be equal to minus 2. Okay, but so if I change the order of this, I'll get the opposite value. In this case, I get 2. Or if I say change the order here, I'm going to get a completely different output. So there's that issue in which I have to be really careful about the order by which I connect this, but I can rephrase this value. So this thing I was talking about, the boundary between value and operation sometimes to blend. So I can write this by 2 plus minus 3 plus 4 plus minus 5. So in this case, I have everything is an addition. And so now this is commutative, like I've seen before. I can swap these around. I can swap 2 and minus 3. I can swap 4 and minus 5. And I will have the same output. Same if I do 2 times 1/3, if I flip this value, and times 4 and times 1/5. Now I can also swap these as I like, and the output will be the same. So as an example, I'm going to do this here with add 4. And I'm going to get the opposite of 3 and 5. And to do that, instead of using the subtract node, I'm just going to use the side node to flip the sign. So 3 becomes minus 3 and 5 becomes minus 5. So if I plug all of these in here, you can see that I get minus 2, just like in here. But now, I can just swap the order of these operands, and I always get minus 2, regardless of their order. Well, something went wrong here. I connect this 1 2 times. Okay, so this is another thing that is useful to inverse values, so that you can convert these operations into all, in this case, all of them are addition and all of them are multiplication. I'm going to also look into notation of inversion. So many times, the usual notation of inversion is something to the power of -1. This can mean for a value or also for an operation. With a value, if we can see that if I try to apply this onto a value, actually what it's going to do is it's going to do the reciprocal. So this will be equal to 1 over the value, and we can check that easily by coming here to instancer points. I have here an instance setup. I'm going to go to the nodes, and so I have these instances on the x-axis, and if I click here, you see them disappear and show up. So I have 2001 instances, and I'm using their x position to plug on the y offset and check whatever happens to the value. So in this case, nothing happens, because when my input is 2, my output is also 2. So nothing is happening to the value. But if I come here and I apply, say, this, so let's see, divide, scalar, 1 over my value, I get this, right? And so this is what the graph of the multiplicative inversion looks like. And if I use, let's say, a Kitazagi power node, and if I put in here to the power of -1, you can see that I get the same as exact thing. So this is for values. This notation for inversion is actually the reciprocal or the multiplicative inverse. For operations, it kind of, it means like inverse action. So if I have an operation and it's inverse, I'll have something like, say, if I add something, the inverse will be to subtract something. If I divide by something, the inverse action will be to multiply by that something. Or if I have something to the power of 2, the inverse action will be to have the square root of that. So in this case, it means, inverse operation, inverse action. And we can look at these. So here, if I try to graph the additive inverse, I can use the subtract node, and the graph will look like this. So 0 minus my value, it's going to look like this. Or I can just use the sign node, scalar sign, like you've seen before. It's a bit more obvious about what it's doing. And here it's the multiplicative inverse that we've seen before. And I can also do here the power of 2 using Akira Sasagi node, say power of 2, and it's going to look like this parabola. And to do the square root, I can use this square root node by Akirazagi also, and it's going to look like this. So in this case, we have the negative instances disappearing because square root of negative values, it's undefined. But I can also do the square root by using a power node. I just have to on the power, instead of putting 2, I have to put 1 over 2. And by doing that, I get the same result as the square root, as you can see here. Now, you'll notice one thing is that with the divide node, there's a case in which we have that. So for example, with the division, when I do something divided by 0, this is undefined. This should actually give me an error. And here in Lightwave, the node does not give you an error. So if I do 5 divided by 0, it actually gives me 0. But it should be undefined, and this is very easy to understand. Let me put here 1 divided by my values. And you can see that as the values come in from the negative side and they come closer to 0, they shoot down to negative infinity. So they go really all the way down to negative infinity. While when they come from the positive side, they shoot up to positive infinity. So the question is sort of, okay, so if to the left of 0, the values shoot up to negative infinity, and to the right, they shoot up to positive infinity, what's in between? Well, the answer is, well, it's undefined. But this can be problematic, as it will cause errors in your evaluation of the node tree. So as we can see here, when I try to do the square root of negative values, the instances just disappear. Or if I come here and I put -4, right, this gives me this message that the value is undefined or is not a number. And so whenever I plug this on to subsequent operations, it will just break the evaluation of the node tree, and that can be problematic. So the way that the Lightwave node does is, by default, instead of throwing an error, it's going to throw 0, and it's kind of understandable, right? Between negative infinity and positive infinity, the midpoint is 0. But maybe you don't want that, because we've seen that 0 can be problematic because it's not scalable. So another way to avoid this, or to change the behavior that the divide node has, it's again to use a logic node and to check if you're trying to divide by something that is equal to 0. If so, you can output the identity 1. If not, then you can just pass the division, because it's all right. You're not trying to divide by 0. And we can see the difference by, let me here hide the grid for a moment. So if I just plug this in here, you'll see that in this instance here, which the x position is 0, the divide node is outputting 0. If I plug this in here, then I'm outputting 1, because I use the logic node to control what's the default value when the value is 0. Of course, I can put 0 as well, like the divide node, but the idea here is to have something else that might beneficiate my calculations. So that's a note on the division. And another thing about inversion, I talked about this notation here, but we have a node in Lightwave called invert, right? have this scalar invert node. And what it does, it's nothing, it doesn't look like anything that I've talked up to now. So it looks like this. Let me put the grid up again. And so this is my neutral graph, right? And this is what invert does to it. So it goes like this. At 0, I get 1. At 1, I get 0. And beyond that, the values are clamped. So what actually does Lightwave invert node performs? Well, you can think about it as Photoshop invert, and that's why I think they used the name invert for that, because it's very Lightwave nodes are very geared towards rendering. So it's like you're inverting some data. And so what it does, it's like in Photoshop invert, what's black becomes white, what's white becomes black, and everything in between adjusts. So if I have a range that goes from 0 to 1, I just basically have it fit a range that goes from 1 to 0. And that's basically what's going on. So you can also think about it as the complementary value in the unit range. So we have the unit range that goes from 0 to 1, and say I have a value that falls in here. Let's say this is 0.2. Well, what the invert node will do, it's give me the remainder value that I need to get to 1. So in this case, it's going to give me 0.8. Of course, to the left of 0, it's going to give me 1. And at 0, it's also going to give me 1, because the remainder for me to go to 0 to 1 is 1. And at 1, it's going to give me 0. And to the right of it, it's going to give me 0. So it's a bit overcomplicated, something that is simple. But to reproduce this, you just need to use, say, a subtract scalar, and you're going to subtract the complementary value to 1, and then you just clamp it. So there's no value that will go beyond 1 or beyond 0. And that's it. This is basically what the Lightwave invert node is doing. So this is about inverse operations. Next, I'm going to talk about how to use them to compare values and extract transformations.